We're going to look at numerical methods. This will be a bit of a recap, hopefully, for most people. It may be a bit new to some people who've not yet seen it in their classes. To start with, as I work through this, you might find it helpful to pause the video and work through the tasks as we go along. Make a sketch to identify solutions to x squared equals 2x at 3. Chances are, if you've made this sketch, you will have x squared minus 2x minus 3 equals 0 as part of your working out or the way you're thinking about it. There are two different ways to look at this sort of thing though, and either thinking of this as a single quadratic graph or looking at it as a quadratic graph crossing a straight line. Both of those work just as well. In fact, this particular graph, I've used y equals x squared graph and a y equals 2x at 3 graph. The point that's being made here is that if you're solving an equation, it doesn't have to be in the form something equals 0. You can see solutions to an equation by putting the bits of the equation on two different sides and then having two different graphs. This really comes into its own when we're looking at functions like these examples. We're not asking you to solve these. They're hard to come up with proper solutions to. In fact, none of these are equations that I could solve. They're equations we could find numerical values that were close-ish to the solutions for, and that's the purpose of this chapter. But they're not graphs you could easily sketch. If you were trying to sketch y equals sine x minus x squared, that's a really hard one to get your head around. But you can sketch y equals sine x, and you can sketch y equals x squared, and you can do it on the same set of axes. So pause at this point if you've not done this before, and have a go at sketching the left-hand side and the right-hand side of each graph, and hence work out how many solutions you would expect to have, and possibly have a guess at what kind of size those solutions would be, roughly where you would expect to find them. Okay, here's the first one, sine x equals x squared. You can see straight away from the graph a solution that maybe you wouldn't immediately spot, 0. It's an obvious one once you see it, but also there is another one. It's clear that there will be a second solution because the graph y equals x squared starts out with a 0 gradient and then increases, whereas y equals sine x starts out with a gradient of 1 and then decreases. By the time they get to pi by 2, for instance, pi by 2 squared is bigger than 2, but obviously sine of pi by 2 is no bigger than 1 because it's sine of something. So by that time, x squared has overtaken sine x, but initially they're in the same place, and shortly afterwards sine x is higher than x squared. So we can see they will cross again, and we can even see that it's going to be roughly at 0.9. E to the x equals tan x. Well, generally e to the x overtakes any graph you can imagine, but tan x approaches a vertical asymptote at pi by 2, which means that the e to the x graph, however steep it might be, you can still do e to the power of any number you like, including e to the power of 4, e to the power of 8, e to the power of 25, which means that e to the power of x graph will cross every single one of the branches of tan x. It will have not only an infinite number of solutions to the left, but an infinite number of solutions to the right as well. It'll have a solution in every single interval of width pi. This is a funny looking one, and it will be quite hard for you to do an accurate looking sketch of this, but hopefully you recognized that the quintic on the left has roots at 0, 1, 2, 3, and 4. And if you know it crosses at those 5 places, then you could do a rough sketch. We know it's a positive quintic, so just like with a positive cubic, it starts low and it ends high. Think about what happens when you raise a large positive or a large negative number to the power 5. Because it's an odd power, the sign is preserved and negatives remain negative and positives remain positive. Asking where this graph crosses the line y equals 1, it's not immediately obvious that it will cross in more than one place, but according to my graph, which obviously I cheated and used GeoGebra for, it's clear that it in fact does. It crosses in 5 places. Depending on the height of those maximum points though, potentially it could have crossed in only 3 places. like if I put an equals 2 on the right hand side, or maybe in only one place if it had been equals 4. And if we were a little careful and we had some repeated roots, we could have equals, I don't know, maybe 1.4, and it would just touch the second maximum point at the top. So a few uncertainties with that one about exactly how many solutions you might get before you start investigating, but you could plug a couple of numbers in, try putting a half into the left hand side, try putting 2.5 in, and you'll probably find you get values bigger than 1, which would convince you that there will be solutions within those ranges. ln x equals 1 over x. This is good practice. See if you remember all of your various graphs. If you can draw y equals 1 over x, you'll find that it has a branch in the upper right quadrant and also one in the bottom left quadrant. ln x only appears on the right hand side. You can't do ln of a negative. If you do ln of 1, you get 0. And it's clear that because 1 over x is always decreasing to the right of the y-axis, and ln x is always increasing to the right of the y-axis, although they will cross once, they will never cross again. So there is a value, there is a solution to it, and it's somewhere a bit less than 2 from the look of this graph, but that's the only solution. Now here's the fundamental idea behind looking for solutions on a graph. If the function you're looking at is continuous within a given interval and it changes sign, then it must be equal to 0 at some point in between those two values. So for example, with this one, e to the x equals tan x. If we rearrange it so that it has something on one side and nothing on the other side, like this, then it's a bit easier to see. Instead of thinking, well, is e to the x higher than tan x, or is tan x higher than e to the x, we can simplify that process. Because we're working algebraically, we don't need to worry about having to sketch this graph. We just say, well, when we sub in a number to e to the x minus tan x, do we get a value bigger than 0 or less than 0? If you sub in 1, you get 1.16, and if you sub in 1.5, you get minus 9.6. So provided we know that the graph is continuous between 1 and 1.5, then we can say for certain that it must cross the x-axis at least once between those 2 points. The continuity condition is important. It's a classic extra question that they'll put in there. You need to make sure, in order to get the full marks for this, it's not enough just to say there's a change of sign and therefore there's a root. You need to say there's a change of sign and the function is continuous in the interval. But that final step there is a change of sign, therefore the root alpha lies between 1 and 1.5. If you think about it, what this is saying is, if you draw a graph without taking a pencil off the page, there's no weirdness like asymptotic behavior like a tan x graph would have near 90 degrees or near pi by 2. If we're somewhere where the graph is sensible and continuous, you can't go from above the x-axis to below the x-axis without taking your pen off the page unless you go through the x-axis. Maybe you go back and forth, you go through it 2 or 3 times, maybe you dip, touch it, come back up again, and then come back down. But at some point, to go from positive to negative, you have to go through the x-axis. You can't go from 100 meters above sea level to 200 meters below sea level without going through sea level. You have to, at some point, go through the surface of the sea. Okay, now we're going to talk about the Newton-Raphson method. This is a more efficient method than bisection. Bisection is the method that you've used before. You've done it at GCSE. If you know that 1 is too small and 1.5 is too big, and there's a solution between the two, you would next try 1.25. Maybe that's still too big, you try 1.125. Maybe that one's too small, you go halfway between your two closest upper and lower limits. So your best upper bound and your best lower bound will give you your narrowest range, and you go halfway each time. Well, the Newton-Raphson method is an improvement on that. It uses a fundamentally different idea, and it looks like a slightly scary formula, but it's not too crazy. You can even derive it for yourself. It's important that you have a sense of what it means as well as just the formula. The formula itself is provided in the formula book, and you'll be expected to be able to apply it, but also to interpret and critique, because there are situations under which the formula will not work. So here's the important idea. If you have a point on the curve and you know the gradient at that point, you draw yourself a tangent line from that point and you find where that line crosses the x-axis. Wherever that is your new x value. So this is an iterative process. It's a way of finding a better approximation to the solution. You already have a number that you think is pretty close to the true solution. Well, sub it in, and sub it into the gradient of the curve, produce for yourself a tangent line, and find out where that tangent line crosses the x-axis, the line y equals 0, and what you'll have is your new x coordinate. Now if you do all of that algebraically and you simplify, you rearrange a bit, you can produce this formula. The new x value is equal to the old x value minus the function at that x value divided by the gradient at that x value, f of xn over f dashed of xn. Here's what it looks like in practice. If we think that minus 1.7 is close to our root, we're looking for a root which according to this diagram is probably at minus 2 and a bit. But if we start with minus 1.7, we can find f of minus 1.7 by substituting minus 1.7 into the function. Now if we can also differentiate the function, we can substitute minus 1.7 into the derivative, which means we could find the gradient. And if we have the point and the tangent, if we have a point and the gradient, we have enough information to find the tangent line. If we look at where the tangent line crosses the x-axis, that's our new point. This is our new approximation for the solution. We call it x1 if we've just started with x0. And you could do this again, and you will produce for yourself another x ordinate, which will be even closer in theory to the true solution. This process works really well, but there is a potential downside to it, which is why generally speaking computers, when they apply this kind of process, they will first apply bisection a couple of times to get reasonably close to the root, and then to get a really rapid homing in on the true value, they will switch over to a Newton-Raphson method. The issue happens when you're close to a stationary point. If you consider what would happen if our x0 value had been just a little bit further to the right, in fact the further to the right we go, the worse our second approximation will get, because the tangent line will be less and less similar to the root down to the root, and it'll be more and more horizontal. If you actually go directly at a tangent to a stationary point, it'll be a perfectly horizontal tangent and it will never cross the x-axis. So you certainly can't go at a stationary point because the entire thing breaks down. You can even see that within the formula. You'd be dividing by f dashed of the x coordinate of a stationary point. Well, the definition of a stationary point is a point where the gradient is 0. So you'd be dividing by 0. And that's why you wouldn't be able to generate a value from it, because the formula would break. But the true underlying reason why the formula breaks is what they're normally looking for when they ask that question in an exam. The reason is that tangent line being created will be horizontal because you're at a stationary point. And it's also important to recognize that even if you're not quite at the stationary point, but if you're close to it, then your next iteration, the new x value you produce, will likely be way off, because even if the tangent line is not perfectly horizontal, if it's close to horizontal, it's going to take you a long, long way away from where you want to be. We're just going to work through an example so you can see what it looks like in practice. It's not as scary as the formula might make it appear. We have a function, and it might be a messy looking function, but it should be something that you can differentiate. And then we're given a point A, which is a stationary point on the curve. We're also told that there is a root in the interval 1.2, 1.3. And the first question is, explain why x0 equals q is not a suitable value to use as a first approximation when applying the Newton-Raphson method. When does Newton-Raphson break? It breaks if we're at or close to a stationary point. But it breaks if we're at a stationary point. It's inaccurate if we're close to a stationary point. Well, what is Q? It mentions Q, it's the x-coordinate of the point A, a stationary point on the curve. So the first point we need to make is that A is a stationary point. The gradient of the tangent will be 0, so the tangent will never cross the x-axis, and it's not possible to calculate the value of x1. For part B, in order to apply the formula, we're going to need the derivative of the function. So we look up at f of x and we differentiate. Remember, you bring the power down in front and reduce the power by 1 when you differentiate a power of x. 1 over root x is also a power of x. It's x to the power of minus a half. So when you bring the minus a half down in front and reduce the power by 1, we get minus a half times x to the minus 3 over 2. The e to the minus x term, e to the anything, differentiates to e to the same anything, but you always multiply by the derivative of the anything. In this case, the derivative of minus x is negative 1, so you multiply by negative 1, and that's why I have plus e to the minus x. You can substitute 1.2 into that, because we care about the derivative at that particular point. They said to use 1.2 as our first approximation. If we substitute that into the derivative function, we get a value. We also substitute it into the original function that was given to us at the top of the question. Now we've got the value for that as well. The reason we need those is because we've had one eye on the formula book and we know what the formula is for the next value. X n plus 1 just means the next x value. So if we want to find x1 and we already have x0, we need x0, f of x0, and f dashed of x0. Substitute all of those in and you'll generate a number. And we can verify that that's sensible by looking at the question. It says there is a root between 1.2 and 1.3, and the value we get is between 1.2 and 1.3.